So I'm going to be presenting my data and findings for Lab 1 constant motion. For Lab 1, we were to analyze the constant motion of an object and compare it to a computational model. I chose to analyze a basketball, and my general method was that I recorded a video of a basketball rolling across the room at constant motion, and I inputted this video into Tracker where I was able to plot position and time points and interpret that data, as well as use it to recreate a computational model in GlowScript. The general principles I used was the position update formula as well as Newton's second law, which is not listed here, but it is implied as we were using constant motion and therefore net force was 0. And finally, I used Tracker, GlowScript, and Excel for my programs. And to list a couple of assumptions for my lab, I assumed that friction was negligible, that the ball moved in a straight line, and that it moved at perfect constant motion. This is the video I used that I inputted into Tracker. It is obviously a ball rolling across the floor at relatively constant motion in a relatively straight line. And on the next slide, I'm going to show you what I did with it in Tracker. This is my video in Tracker. I used the diameter of the ball, which is roughly 0.22 meters, as my scale, and I aligned the axes right in front of the ball so that every 0.01 seconds, which was my time interval, I could plot where the ball was, and Tracker could create a position time graph and get my data for me. This is my video in I then used my data from Tracker to create a computational model in GlowScript. So I changed the initial position of the ball to 0.0055 and the initial velocity to 1.6053. I also changed the delta t to 0.01 so that it matched the time intervals used in Tracker, and I changed my max time in the while loop to 0.39 seconds, which was how long my video was. And this was what allowed me to create a computational model to predict the motion of the ball. Using the data from GlowScript and Tracker, I was able to create an observed and predicted position versus time graph. So I took the time intervals from Tracker as well as the points plotted from Tracker and plotted it with the position points from GlowScript. And so this allowed me to create a comparison graph that you see here. The light pink line is the observed position and the purple line is the predicted position. As you can see, the lines are fairly similar, which basically means that my computational model in GlowScript pretty accurately predicted the motion of the basketball from the original video. In conclusion, I'd like to answer some of the questions associated with Lab 1, the first being about flipping the axes. So if I was to flip the axes, all of the position data would be in the opposite direction, but time would remain positive, seeing as it is a positive scalar quantity. For example, if I flip the axes from positive x to negative x, the initial and final positions would all be negative, time would be positive, and therefore velocity would be negative. And the second question was about forces. It is possible to say how many forces there are added together to give a zero net force. For example, the force of the hand on the ball would be in the same direction as the ball, and friction would be in the opposite direction of the motion. I stated earlier that friction was assumed to be negligible in this scenario. This is not a realistic case, but ideally the two would cancel each other out and result in a zero net force. My computational model was very accurate in predicting the position of the ball based on my Tracker data and the original video, and I hope you enjoyed watching my presentation. Thank you.